Okay, welcome back. So this is one of the easiest question that we're going to be working together in terms of the inclined plane. As this time it's similar to the most recent video that we have, but this time there is no friction. There's no friction, and all we need to do is figure out what is the difference in terms of the applied force if there's no friction. Okay, so here's what we're going to do. My suggestion is we will use every step right here. Okay, we will use every step right here, but all you have to do is remove our force of friction. So that's my advice. Remove our force of friction. Okay, so remove our force of friction. Now, what is the minimum amount of force that is required for us to apply in order to figure out, so to cause not the object to move, to cause the object to stay at rest? Okay, so all we have to do is remove the force of friction in all of our equation, and then we will be able to come up with an answer, which is mg sine theta. But let's see if we can derive it. Okay, so let's see how do we derive it. So again, same status, same way, same step. Let us draw our x and y coordinates. The imaginary one, the intersection, will be our dot that we are going to use for our free body diagram. So let's place it here for FBD, or free body diagram. Okay, so free body diagram, same dot. We have our friction. We have our force of gravity or weight. We have our normal force, Fn, normal force, and then since there's no friction, the only force that we have acting that is applied is our applied force F, which is along this y-axis, along the x-axis. Okay, so let us proceed with a solution. Proceed with a solution. Let's put our dot, and then we have our force of gravity, which is mass multiplied by the acceleration due to gravity, and then we have our normal force right here, Fn, and then of course the force that we applied, F. So there are some forces acting along it. Okay, so here's our y-axis. Let's use the red ink along the y-axis. So that's the y component, and here's our x component. So this is our fgx or fgy, and here's our fgx. We all know that fgy is mg multiplied by cosine theta. And again, the reason why we're using cosine instead of sine, it's because your angle is measured along the y-axis. And then we have fg of x is simply mg multiplied by sine theta. So therefore, going to the next step of our free body diagram, as we're moving faster compared to the previous question because now we know what we're doing. So again, Fg, which I missed, so this is our Fgx, and here's our Fgy, here's our force, the applied force, and here's our normal force. Fn. As I mentioned earlier, Acceleration, both axes, they're not moving, so the acceleration along the y-axis is 0. The acceleration along the x-axis is also 0. So if we apply Newton's law of motion, summation of forces along y is mass multiplied by the acceleration along the y-axis. Forces going up is positive, that is normal force minus Fg sub y equals mass times the acceleration, which is 0. The normal force is simply minus mg, since this is your y, that is cosine theta, equals 0. So the normal force is simply equivalent to the y component of the force of gravity. It just so happened that's the opposite direction. Cosine theta. Summation of forces along the x-axis is mass times the acceleration along the x-axis. Any force going to the right is positive, so that's F minus Fg sub x equals mass multiplied by 0. So that will give us force minus mg sine theta equals 0. So therefore, the amount of force is simply equivalent to mass times g sine theta. Technically, you don't have to work on the y-axis, okay, on the y component. However, I just wanted to use this to show that, as I mentioned earlier, all you need to do is to eliminate the friction from the previous solution right here. If you remove this friction, then we have mg sine theta, mg sine theta. Likewise over here will be the same, mg cosine theta. So thank you. That will be the end of this video. It's very short. The solution for this problem is not as complicated compared to the previous solutions that we have made.